Okay, so in this video, let us look at the commutative property for the different numbers. Now, we have already learned about the commutative property for natural, whole numbers, and integers. In this, we are going to add to our knowledge of commutativity for rational numbers. Now, just a quick note, what do we mean by commutativity? Commutativity simply means what happens if we change the order of the numbers in the operation, and that is what is shown in the third row that is shown over here, right? The condition for commutativity is that we just check. Let's say when we are checking commutativity for addition, we check when two numbers are added, a plus b, and then we change the order of the numbers. That is, we now add b plus a and see if both of them are equal or not, and similarly for the other numbers. So now let's start looking at the second column here, which gives an idea of the commutative property for the different numbers. Now, as I said, the condition for addition is we first take any two numbers. In this case, I have taken a and b. So we first add a plus b, and then we add it in the other order, that is, we add b plus a, and then we compare the result. If both of them are equal, then we say that that particular set of numbers or those numbers are closed under the operation of addition. So now I just wanted to review that we have studied about the commutative property for addition for natural numbers, whole numbers, and integers, and we concluded that these three numbers are closed under the commutative property, which simply means that it doesn't matter the order in which you add two numbers doesn't matter. So you could add two natural numbers in any order, you would still get the same results. In fact, it applies not only for two numbers but for any numbers. You can add any amount of numbers or n numbers, different natural, whole, or integers, and the results will be still the same. Okay, so now in the rational numbers, we will later on prove in the second video that rational numbers are also closed for the property of addition. So you can see that the smiley face means that they are closed. Now let's look at the subtraction, the commutativity under the operation of subtraction. So for the natural numbers, whole numbers, and integers, we concluded that these numbers are not commutative under the operation of subtraction, which means a minus b is not equal to b minus a. Here is the condition: a minus b is not equal to b minus a for these sets of numbers. Now, for rational numbers also, we will find out that these are not closed, or these are not commutative. They do not follow the commutative property under subtraction, as is shown over here. So in essence, we can conclude that all the four numbers that we have learned, natural numbers, whole numbers, integers, and rational numbers, they are not closed. As you can see over here, they are not closed under the operation of subtraction. It's not okay, sorry, it's not about being closed. They are not they do not follow the commutative property under the addition under the property of subtraction. Okay, now let us look at multiplication. So for multiplication, all we do is we multiply two numbers, a multiplied by b, and then we multiply it in the other order, that is b multiplied by a. And we already found out that for natural numbers, whole numbers, and integers, they follow the commutative property for multiplication. However, rational numbers also follow the property or are also commutative under the operation of multiplication. So we can conclude that all the four sets of numbers, natural numbers, whole numbers, integers, and rational numbers, follow the commutative property for multiplication, which means that you can multiply any of these numbers, that is two integers or two or more than two integers, in any order, you will still get the same result. Now, if we look at the last column, that is division, and here the criteria to check the commutative property for division is you just divide two numbers. Now, a divided by b. So please note, when I say a by b, so a is actually a type of a number here. So when we apply this condition that is shown over here, let me just, yeah, this condition that is shown over here. So a is actually a type of number. Let's say, if we are taking rational numbers, a is a rational number and b is another rational number. Okay, so a divided by b, if it is equal to b divided by a for all the numbers in a particular number system, then we say that it is closed under division. And if you look at the smiley faces which are crying over here, which means that all these numbers, they do not follow the commutative property for the division operation. So to conclude our observations on these tables, then all the four types of numbers that we have studied so far, that is natural numbers, whole numbers, integers and rational numbers, they follow the commutative property under the operations of addition and multiplication. And all four of these numbers, they do not follow the commutative property for under the subtraction and division operations. So what it simply means, when we will be doing the sums later on, is the fact that you could add or multiply all these numbers in any order without having a change on the result. But if you try to do subtraction or division by changing the order of the numbers, you may get a different result. Okay, so in the next video we are going to learn the proof for the commutative property for rational numbers.